Alright crew, welcome back. We are going to continue our journey into Extrema by today delving into a new topic called the first derivative test, or the FDT for short. What this gives us is a nice way to characterize maxes and mins and saddle points without having to have a graph in front of us. But to build up the concepts, we're going to deal with graphs, or pieces of graphs first. Over here I got a batch of relative maxes. One's a smooth little hill, sharp point up there. Next I got two relative mins, bottom of a valley, nice and smooth, and a very sharp cusp right there. In both cases, two maxes, two mins, and lastly, two saddle points. Now I want to characterize maxes first, but in terms of their slope properties. What is the slope? Just to the left of that maximum point. Is it positive or negative?
That's a positive.
Positive. We can keep going for a few more slopes. Positive, 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 just to the left of my max. And look, same deal here. Even though there's a sharp point, positively sloped. That is the theme to the left of a relative max. What is the theme to the right of a relative max?
It's also negative.
Then it transitions to being negatively sloped. So just to the left, it's positively sloped in red, and then just to the right, it becomes negatively sloped. What do you think the pattern is for relative mins? What are the slope properties of relative mins?
It'd be the other way around. It'd be a negative slope on the left.
Right, and to verify that,
right.
Just to the right, or just to the left, it's a negative slope. I'll denote that in blue. Same deal here for the sharp point, negative slope just to the left, but to the right the slope trend reverses. Becomes positively sloped. Excellent. Now what about for saddle points? Let's stick with this first little piece of a graph here. Aside from this point right there where the slope is 0, the slope of this piece is always what?
Seems like it's always negative, right?
It does seem that way, yeah. There it's a bit verticalish. But yeah, aside from the saddle point itself, the slope is always negative. There's no change happening, no transition. And likewise for this second saddle piece, aside from the saddle point itself, the slope everywhere else is
Positive.
positive.
So you did the red for positive and blue for negative?
Yes.
Nice.
Yes. So notice for relative extrema, relative maxes, and relative mins, you see a transition. For relative maxes, positive to negative sloped. For relative mins, it goes from negatively sloped to positively sloped. But you see no such transition with saddle points. So we can summarize that here in this nice little column. F prime, which is the slope, right? The derivative reports on the slope of our function. So here's plain old f. Here's f prime. F prime, the slope, in the case of relative maxes, goes from being positive to what?
Negative.
Negative. Likewise, the trend for relative mins, negative slope to a positive slope, yes?
Yep.
Absolutely. Now what is the trend finally for saddle points?
Positive to positive or negative to negative?
In other words,
None.
no change.
Yeah.
No change immediately to the left or the right. So that's the idea. And the way you can distinguish, we'll look at this more when we deal with computations. We can generalize this first derivative test even further to determine what are called domains of increase and domains of decrease of your function. So let's go on to the other side of the world. Now here I don't have just a piece of a graph. Let's say I have the entire function itself. The entire function itself, going over to the left, it shoots straight up. To the right, it just shoots straight down forever from that point on. But notice I have labeled my two critical points, yes? These are places from our critical points, are places where the derivative of the function is either undefined or 0. So it's 0 there and there.
I have a question about critical points.
Yes.
On the last graph with the saddle point, does that count as a critical point, or is that not a critical point?
That's a critical. No. Are you talking about the sharp point or the saddle point?
The saddle point.
The saddle point, that is considered a critical point.
Okay.
So remember, relative extrema only occur at critical numbers, but not all critical numbers indicate relative extrema.
Okay.
That was one of the key takeaways from our last little lecture.
Okay.
Now here, from A to B, what is my slope always doing?
It's always increasing.
Well, it's not always increasing, but
Well, it's
always
positive, but it starts decreasing, right? Well,
No, we'll talk about the rate of change in a future video, but for now, from A to B, the slope of your graph is always
positive.
positive.
Yeah.
What about from negative infinity to A?
That's always negative.
Always negative slopes, so little segments like so. We can do more segments like so, from B to positive infinity. Notice these are also negative slopes, yes. So let's see. This is where I want you guys to get in the habit of putting this information in interval notation. My first interval for negative infinity to positive, not positive, I meant
A.
just A. The second interval is from A to B. And the last interval is from B to positive infinity.
Okay.
So, in general, your critical numbers immediately give you a way to partition, all the real numbers. They immediately set up intervals for you, just by knowing them. On this interval, A to B, the sign of your first derivative is always
Positive.
positive. From B to positive infinity, the sign of your first derivative is
Negative.
negative. Likewise for this one, negative infinity to A. Negative as well, yes?
Mm-hmm.
Now for this next row, the behavior of just plain old f, I'm really getting at whether it's increasing or decreasing.
Okay.
On that end. So loosely, all I want you guys to do is, I want you to internally define increase and decrease in terms of what is it doing left to right. So for this piece here, when you go left to right, is this function increasing or decreasing?
It's decreasing.
It's decreasing, so I'm going to just say DEC for decreasing. What about from A to B?
It's increasing.
Yes, again, it's always defined left to right. Left to right, it is increasing. And finally, for B to positive infinity, it's decreasing. And so we can determine then, that if you just knew this chart, if you didn't have a picture and just had this chart here, if you had this information in front of you, you can say immediately that, oh, okay, because the slope right immediately to the left of A is negative, and the slope immediately to the right of A is positive, I know that AF of A is what kind of extreme?
Relative minimum.
Yes. Is a relative minimum. Again, if you just knew this chart and didn't have that picture, you could still conclude this. You could also include that BF of B is what?
Relative maximum.
Yes. A relative max for the reason that it transitions from being positive sloped immediately to the left to negative sloped immediately to the right. And broader, it's decreasing, increasing, and decreasing on these intervals. Now, we're going to look at some functions here in a bit where the intervals that are immediately set up by your critical numbers aren't necessarily the intervals of decrease, increase, and decrease. Specifically, those happen in the case where you have what are called vertical asymptotes, where the argument's a little more technical, but for the most part, when you don't have vertical asymptotes, the intervals set up by your critical numbers immediately correspond to your intervals of increase and your intervals of decrease. Okay. Now, before moving on, here's a technical definition of what it means to increase and decrease. A function f, we say it is increasing on an interval I, an x interval I,
Okay.
if for any 2 points or x coordinates you pick, let's say x1 and x2, as long as x2 is greater than x1, then if f2 is greater than f of x1, we say it is increasing. So,
Yeah.
again, pick any 2 points. Say this will segment here from A to B. Pick any 2 x coordinates. Let's say there and there. Say this is my x1, this is my x2.
Yeah.
Since x2 is greater than x1, if it's true that f of x2 is greater than x1, then it's increasing. And an increasing function has to satisfy that for every possible pair of x coordinates you pick. And of course, we have a very similar definition for a function decreasing on interval. But all you do there is just, you keep everything the same in the definition, but you swap the direction of the inequality. So, for example, from negative infinity to positive a, pick any 2 x coordinates, let's say this one, call this one x2, this one x1. If f of x2 is less than f of x1, for any possible pair of x coordinates you pick, that function is always decreasing on that interval, which in fact it is.
And you just put it simply before it by saying if it gets lower when you're looking at it from left to right, that would be decreasing.
Yeah, the loose way to remember this is just read it left to right. Left to right, is it decreasing? Yes. So we say the function is decreasing. Left to right, is it increasing on this interval? Yes. So we say it's increasing on that interval. That's just the loose way of remembering this more technical definition. Okay, now let's put these ideas into computational practice with this question here. We got a function, x squared plus 12x plus 32. We want to find the critical numbers of it. We want to find the intervals of increase and decrease of it. And we want to use that information to find and classify all the relative extrema. So after we find the relative extrema, we want to be specific and say it's a relative max or relative min, or it could be a saddle point. Now, I know you guys know that this is a quadratic. Pretend we had no idea what this graph looked like, and let's just use the tools of calculus to answer this question. What is the first thing I have to do?
We need to find the critical numbers, so we need to take the first derivative.
Absolutely. F prime is
2x plus 12.
2x plus 12. And for critical numbers, you set this equal to
0.
0 or undefined, but is this ever undefined?
No.
No. So we only have to worry about setting it equal to 0. And that happens when x equals
Negative 6.
negative 6. If you plug negative 6 back into the original, is it defined at negative 6?
Yes.
Okay, so that is a critical number. So just a quick recap. In order for something to be a critical number, it has to not only make this derivative either 0 or undefined, it has to also be defined in the original function.
So asymptotes, vertical asymptotes will not be critical numbers, right?
No.
Okay.
No. So negative 6 is my critical number. And once I get that critical number, what do? What's the new thing we discussed just now?
You find out whether the values to the left of it are positive or negative, and the values to the right of it are positive or negative.
Right. I just use those critical numbers to set up nice intervals for testing. So negative infinity to negative 6, and negative 6 to positive infinity. Let's say here's the sign of f prime. And under that, in the next row, I'll say behavior of f. Just plain old. Alright. Take any old number you want from here, throw it in f prime, and answer me, do you get a negative or a positive value?
You'll get a negative value.
Yeah. Like negative 100, stick that in there.
Mm-hmm.
It's going to be some negative number.
Yeah.
Likewise, if you take a number from in here, let's say something really, really positive, throw it in for x, and you get
A positive number.
a positive. In other words, to the left of negative 6, remember, the slope is 0 at negative 6.
Mm-hmm.
To the left of negative 6, the slope is negative. To the right of negative 6, the slope is positive. And that's a hallmark for what kind of extrema?
Relative minimum.
Yes, relative minimum. And moreover, the behavior of f, if the slope is always negative for this piece, then it has to be always
Decreasing.
decreasing. Likewise, if the slope on the graph is always positive over an interval, it is always increasing.
Yeah.
from all this information in total, we know that -6, f of -6, is a relative minimum. Let's go ahead and compute what f of -6 is. That's going to be -6 comma, throw it into the quadratic.
36 minus 72 plus 32. So that's 68 minus 72. I think that's 4.
4.
Negative 4. Negative 4.
Yeah. -36 plus 32, -4. That is the minimum point on this graph, and now falling back to resurrecting our knowledge of Algebra 2 and pre-calc. This is a quadratic, and this point here is the what of that parabola?
Vertex.
Yes. So somewhere in the third quadrant, and then it shoots up. Now clearly for parabolas, they only have one relative extrema. It's either going to be a min or a max. In this case, for an upward facing parabola, the slope immediately to the left is negative, and the slope immediately to the right, or always to the right, is positive. So that is true for any upward facing parabola. You will always see that slope trend. Now I said last time that for the most part, your critical numbers, the intervals they partition for you, are almost always going to be the same as the intervals of decrease or increase. There's almost always going to be a one-to-one correspondence. The only case where that's not true is in the following example, when you have vertical asymptotes. Yeah. So same set of instructions. I want to find the critical numbers. I want to find the intervals of increase and decrease. And then I want to find and classify all extrema. So let me take the derivative of this to get the critical numbers. We apply the quotient rule. Low D high minus high D low. What's the derivative of the low?
Just 1.
Just 1. All over x plus 1, the whole thing squared. Let's make some room to gallop here. Now let's see. From this, I can factor out a 2. I just want to see if there are any tricks I can use to minimize the amount of algebra I have to do. So I pulled the 2 out of this 2x minus 2, and I'm left with an x minus 1 there.
Right.
And this whole thing here I can factor into
X minus 1 squared.
x minus 1, the whole thing squared. That's all over x plus 1, the whole thing squared. And now let us look at the numerator. Do you see anything common to this first term and that second term?
Yeah, an x minus 1.
Yeah. So we can pull on out an x minus 1, like so. And we're left with a 2 times x plus 1 minus the leftover x minus 1, yes? And of course the x plus 1 squared remaining in the bottom. Now someone help me out. What is this inner term, this bracketed term, the entire thing? That's going to be
2x plus 2 minus x plus 1.
Okay, so I'm left with just 1x. Now what's the number I'm left with?
2 plus 1, so 3.
Yeah. 2 minus negative 1, x plus 3. So I'm running out a little shortened space here. I'm just going to replace this entire bracketed term with x plus 3. Now, isn't this much nicer to look at than the initial setup?
Yes.
X minus 1 times x plus 3 all over x plus 1, the whole thing squared. I think this is a fine time to test for critical numbers, don't you?
Yeah.
When is this thing equal to 0?
When x is 1 and negative 3.
When x equals 1 and when x equals negative 3. Now again, key thing. Are these defined in the original?
Yes.
Right, they don't make the denominator 0.
No.
So they're good. These are both critical numbers. Check, check. They are defined in the original. How about if I set this equal to undefined? This is undefined when
X is negative 1.
x is negative 1. Is negative 1 defined in the original?
No.
No. Then because of how I defined a critical number, this does not count as a critical number, yes?
Right.
Right. So you may think, okay, hey, these are the only critical numbers. Let's just fall immediately into, I'm going to do this in a different color, in red, because it's really the wrong way of doing this. You might think, okay, let's just fall immediately into interval testing with these critical numbers. What intervals do these critical numbers produce? Well, start left to right. Negative infinity to positive 1.
Negative 3.
Negative 3. And then negative 3 to positive 1, yes?
Yeah.
And then 1 to positive infinity.
You said this was the wrong way to do it?
This is the wrong way. You'll see why in a second here.
Okay.
Let's say, you know what? Let's say behavior of f. Or just f of x behavior. In other words, is it increasing or decreasing?
Okay.
So far the correlation has been, hey, if f is negatively sloped somewhere, that means it's decreasing right there. If it's positively sloped somewhere, that must mean it's increasing somewhere. So we're trying to draw a one-to-one correlation like that, which is almost always true, but you'll see here that's not quite. So let's work with the assumption that it is true. That if something is negatively sloped somewhere, that means it's always decreasing on that end. Okay, right here, pick a number from inside here, throw it in this function here, in the nice factored form, and tell me if you get a positive or a negative value. So let's say negative 10. If I stick negative 10 in this, I get negative 11 times negative 7, all divided by a positive, right?
A negative squared, which is a positive.
Yeah. The denominator is always positive, you're always squaring it, so you really only have to worry about the sign of this product up top.
So that would be positive.
Right, so we'd say, hey, positive slope, which means it's increasing, right?
I believe so.
Now pick a nice number from inside here.
Okay. We can just do 0.
0. If you throw a 0 in here, do you get a positive or a negative value?
A negative numerator, so it would be negative.
Right. Negative implies decreasing. And finally, pick a number from inside 1 to infinity.
If I pick 9 million, I think it's all going to be positive.
Yeah, all positive, so we'll say that's increasing. Now to see why this is wrong, it's not completely right, I'm going to show you what the graph of this looks like. This has a vertical asymptote where?
At 1.
Negative
1, negative 1.
Negative 1. And this thing is actually going to have a slant asymptote as well. Do you remember from pre-calculus, if the degree of the top is greater than the degree of the bottom, you can do some long division and get what's called slant asymptotes. That thing is going to, let's see here. It's going to do something like this. And then we get another piece like so. Here's my x-coordinate of positive 1. Slope is 0 there, yes?
Yes.
Here the slope is
Negative 3.
negative 3. So really I've kind of spoiled the question for you, a part of it. You know, here's the relative max, here's the relative min. But I want to emphasize this interval of increasing and decreasing business by looking at this. So this part here, negative infinity to negative 3, that's completely right, right?
Yeah.
That's always increasing. From left to right on that interval, that's always increasing. And likewise for this very last one, 1 to positive infinity, the slope there is always positive. So on this interval, the function's always increasing.
Gosh. So it's the asymptotes that mess it all up.
Yeah, that asymptote of negative 1 messed this up. Is it true to say that this function, falling apart, this function from negative 3 to positive 1, this is not always decreasing, right?
No.
Yeah, okay, right here at the asymptote, it pops up to positive infinity. It goes from negative infinity to positive infinity, which is the exact opposite of a decrease, right?
But isn't it decreasing everywhere except at negative 1?
No, given the definition of what it means for a function
with the definition, I see.
to decrease, remember you pick any two x coordinates, and then if x2 is greater than x1, then f of x2 needs to be greater than f of x1.
Gotcha.
Which is not true at all for this interval here.
So it'd be decreasing from negative 3 to negative 1,
Yes.
and negative 1 to 1,
Yeah.
but not from negative 3 to 1.
Right, so the correct way of phrasing this is not like this. So that part's not right. That's right, that's right. This part isn't right because of that vertical asymptote. We would phrase it as so. F is increasing, go left to right, negative infinity to negative 3. F is decreasing on negative 3 to negative 1. And F is also decreasing on negative 1 to positive 3.
Positive 1.
Oh, my bad. Negative 1 to positive 1. And finally, F is increasing on 1 to infinity. In other words, when you're doing interval testing to determine intervals of increase and decrease, it's not enough to include just the critical numbers. You have to also include, in your interval testing, the vertical asymptotes. So you have an additional interval to test. So don't forget that. Anytime you see a question, a rational expression, rational function, bear in mind and see if there are any vertical asymptotes, because you'll have to incorporate them in your graphical analysis.
So even though vertical asymptotes are not critical numbers, they're still necessary to find and solve.
Yes, exactly. You need critical numbers and you need the vertical asymptotes. Remember, x equals negative 1 was not a critical number because it made the original undefined, and that's no good given our definition of what a critical number is. Okay, well once you got these, hey, f is increasing on this, decreasing on this, decreasing on this, increasing on this, and you know the slope is 0 here, well this immediately implies, let's say, so this was one of my critical numbers, right?
Mm-hmm.
Negative 3, there's the other one, there and there, there and there. This analysis immediately implies, hey, if it's always increasing on this interval, always decreasing on this interval, then negative 3, comma f of negative 3, is a what kind of extrema?
Relative maximum.
Yes. Relative max. Likewise, if it's always decreasing on this interval, but then suddenly transitions to increasing on that interval, then 1 f of 1,
So go to minimum.
yes, is a relative minimum.
So we have a relative minimum that has a greater y value than a relative maximum. That's interesting.
Right. Remember, relative mins don't have to be absolute mins. And relative maxes don't have to be absolute maxes. So you can have a relative min that's greater than another relative max. You know, and that's what we looked at last time, for instance. For example, this relative min right here, and this little piece I've sketched out, is bigger than all of these relative maxes.
Okay.
Okay, any questions about that? Now, y'all, just to further emphasize that you need to test not only the critical numbers, but places where you have a vertical asymptote, when you are doing interval testing for intervals of increase and decrease, it's sometimes the case where you can have a change of slope and your function doesn't have any critical numbers. So for example, someone remind, what's the graph of 1 over x squared look like?
Would it have an asymptote at x equals 0?
You got an asymptote at x equals 0, so it's kind of like that hyperbola thing, but except instead of the second piece of the hyperbola being in the third quadrant,
It's in the second.
it's in the second. Yeah. So there's the graph of f. Now, I'll get back to that in a second. This thing I can write as x to the negative 2, which would imply that this first derivative is negative 2 times what?
X to the negative third.
X to the negative third, which of course is negative 2 all over
X cubed.
x cubed. Is this thing ever equal to 0?
No.
Is it ever equal to, is it ever undefined?
Yeah.
It's undefined where?
At 0.
At 0, but is 0 a critical number of this function?
No, it's an asymptote.
No, yeah. If you plug 0 back in the original, it's not defined, so it can't be a critical number. But look, clearly, this graph transitions from being positively sloped to being what?
Negatively sloped.
Negatively sloped. In short, it is increasing on this interval and decreasing on this interval. So even though 0 is not a critical number, it's an asymptote, and you want to test asymptotes when you're testing for intervals of increase and decrease. So let's say, so the derivative is positive there, the derivative is negative there, this is an interval of increase, and likewise this is an interval of decrease. Again, the point to emphasize is that I did interval testing not with a critical number in this case, but with a vertical asymptote. That makes sense? Mm-hmm. So that, in a nutshell, that's the essence of the first derivative test. It lets you find, not only lets you classify your relative extrema as relative mins or relative maxes or saddle points, but it also lets you determine intervals of increase and intervals of decrease, so long as you remember when you're determining the latter that you also have to test asymptotes. It's not enough just to test critical numbers. Now let's go around the world to something quite fun, something quite unexpected, and that is
Word problems.
word problems.
Yay.
So the last batch of word problems we did were called related
Rates.
rates. And related rates were essentially just chain rule word problems. Okay? Optimization problems, I want you to think of them as like first derivative word problems. Just like related rates or chain rule word problems, these are first derivative test problems. And we'll also learn something in a future lesson called the second derivative test. But in either case, it's just calculus applied to a word problem. We have two positive numbers, they need to add up to 100. And just given that constraint, given this constraint here, what is the maximum possible value of their product? We can call their product P. P is x times y. And I want to maximize P given this constraint. So some technical terms here. This right here is what's called, said it a couple of times now, the constraint. In other words, you can't just plug in any old x and y. Here you have to plug in only the x's and y's that satisfy this thing. That's the only time you're allowed to plug in.
Would another constraint be that x and y both have to be greater than 0?
Oh, that's another one too. X and y are both strictly greater than 0, yes?
Yes.
They're both positive. And also they're less than
100.
Less than 100. So, and say constraints, plural, like so. This right here is what's called your objective function. It's what you're trying to maximize or minimize. The objective is, in this case, to maximize it. So, any ideas? Given the way it is right now, p is a function of how many variables?
2.
It's a function of 2, but I can utilize my constraint to rewrite it as a function of
1.
1. I don't like dealing with x's, so we can solve for y in order to get rid of y. Given the constraint, y is always
100 minus x.
100 minus x, so p is always
100x minus x squared. Or
Yes.
x all times 100 minus x squared.
and when you distribute that bad boy across, you get 100x minus x squared. When you graph p in the coordinate plane, so let's say p is your vertical axis, x is your horizontal axis, what shape is this going to take?
Parabola?
It's going to be a parabola. Is it going to face upward or downward?
It's going to face downward.
So where would the maximum value of p occur?
The vertex.
On the vertex, yeah, the vertex of the parabola. But let's pretend we don't know the shape of this graph,
Okay.
because really you could do this problem without any calculus, given that knowledge. But let's pretend we don't know the shape. We just know this. What do I do next?
We should find that critical number, so let's take the first derivative and
Yes.
see when it equals 0.
First derivative, dp over dx. Or you can say p prime if you want. First things first, I need to find that derivative. That is 100 minus
2x.
minus 2x. That thing equals 0 or undefined, never equals undefined. I only have to worry about 0. It equals 0 when x is, or let's say 100 equals
2x.
100 equals 2x. In other words, when just plain old x
Is 50.
equals 50. Now again, all I found is a critical number. I don't know, again, assuming I don't know the shape of this graph, I don't know whether this coordinate corresponds to a minimum or maximum or a saddle point. I'm hoping it corresponds to a maximum because that's what I'm trying to find. We've got to verify that with our first derivative test. How do I partition my interval? Now remember, what is the constraint on x besides this?
It's a positive number.
Right, it's positive and it's always less than
100.
yes. So the intervals I want to test,
Are from 0 to 50 and 50 to 100.
yes, 0 to 50 and 50 to 100. I want to analyze the behavior of p on there.
P
So
or
let's-
the derivative of p?
Well, both.
Okay.
What is p prime doing? What is p doing? Okay, really, you only need p prime. But just for the sake of completeness, I'm going to throw p on this second row down here. If you take any number between 0 and 50, throw it into your first derivative, do you get a positive or a negative value?
You'll get a positive value.
You'll get a positive value. If you take any number between 50 and 100, non-inclusive, throw it in your first derivative, you get a positive or a negative value?
A negative value.
You get a negative value. And of course, at 50, the slope is 0, right?
Right.
So it goes from positively sloped to having a 0 slope at 50 to negatively sloped, which is the characteristic of what kind of extreme?
Relative maximum.
Yes. We have a relative maximum at 50, p of 50, yes.
Okay.
But I can go one better than that, right?
Also,
Well, if the slope is always positive from here to here, it's not just a relative max right there. So now we can go and try to graph this. There's my x. There's my p of x. I got holes. Let's see here. When x is 0, what is p?
0.
Right. So again, I'm not defined at 0, so I gotta put a hole. So I'm gonna put a hole right there at 0.
And you have a hole at 100.
Yeah. If I stick 100 in my original, my product, I get
That's
x.
also 0.
100 times 0. But again, x has to be less than, strictly less than 100.
Okay.
So I got a hole there.
Nice.
And now what this is telling me is that the behavior between these 2 points, from 0 to 50, the slope is always positive. Yes.
So it's increasing.
So it's increasing. I mean, it can't go down because that'll be a negative slope. So it has to be doing something like that, then it hits a zero slope, and then it hits a negative slope, and it continues on in a negatively sloped manner all the way to 100. So this isn't just a relative maximum there.
Oh, so it's an absolute max.
It turns out to be an absolute max.
Which is what the question's asking for.
Yes. What is the maximum possible value of the product? And that's P of 50. So absolute max as well. Now someone help me out. What is P of 50?
It'd be 50 times 50, which is 2,500.
Yes. 50 times 50. 2,500 is your final answer. Which makes some intuitive sense, right? If you want to maximize the product of two positive numbers between 0 and 100, have them both be the same right in the middle, makes some sort of intuitive sense. So yeah. So again, this was a word problem, but we made it into a graphical problem using the tools we've been discussing. Cool. Any questions? So continuing our theme here of optimization, we have Cowboy Barkley being in position 800 feet of fencing, and he wants to enclose 2 rectangular adjacent pens like so.
Starting a ranch or something?
The pens adding to my ranch, adding to my heavenly collection. Okay. 2 pens, they share one fence, that's this guy in the middle. And I want to know, given that I have only 800 feet to which to make this arrangement, what is the maximum possible total enclosed area? First thing is first, I should probably do what to this picture?
Label the height and the width.
Yeah, let's say that is an X there, that's an X, that's another X, that's another X. Gotta be the same size, same rectangles. And that's a Y, that's a Y, that's a Y, different lengths. Yes?
Yes.
Okay. Now, given that arrangement, what is the maximum possible total enclosed area? So here is my constraint. I only have 800 feet of stuff to work with. What do you think I can do with that 800 feet? What equation can I set up? Do you see anything promising?
Well, the perimeter of all of that equals 800, right?
Perimeter-ish. I mean, you got that thing in the middle, so it's not really perimeter.
Yeah, the fencing.
All in all, that plus that plus that plus that plus that plus that plus that needs to be
800.
Yes. So 4x plus 3y has to be 800 feet. That's my constraint. So whatever I pick for x, I gotta pick y in such a way that it satisfies this equation. Now then, I'm trying to maximize the total enclosed area. I have 2 rectangles here, yes?
Yes.
What is the area of one rectangle?
Just x times y.
X times y, so the area of both of them is going to be
2xy.
2xy, so we have a equals 2xy. That is my objective function.
Okay.
What can I do next?
Should we write y in terms of x and x in terms of y?
We can do that. And in a second I'll put some inequalities on the board, but for now let's just rewrite this. A has to equal, well, 3y is always 800 minus 4x, yes?
Yeah.
So y by itself is going to be
That all over 3.
all over 3, or we can break it up like this, 800 over 3 times, or minus 4x
over 3.
over 3 for just plain old y. I take this guy, I smuggle him in right there. And so I get a in terms of just one variable, one letter, just x, 2 times x.
Times 800 over 3 minus 4x over 3.
800 over 3 minus 4x over 3. Ooh, and let's see, I can write a then as a difference of 1600x, all divided by 3, minus minus 8x squared over 3, yes?
Yeah.
Yes. And while I'm here, I might as well take the derivative. What is a prime? Or dA over dx?
It'd be 1600 over 3
1600 over 3
minus 16x over 3.
minus 16x over 3. It looks good to me. Looks good to me. Now then, let's see what we got here.
So should we find critical numbers and set it to 0?
We should. We can do that. Before that though, let's, since we're dealing with x, let's set up an inequality for x.
Okay.
X has to be what kind of number since we're dealing with a physical, real-world problem?
It has to be a positive number.
It has to be positive.
Less than 800 over 4. So less than 200.
Yes. So it has to be strictly less than 200 because if it equals 200, then I get 4 times 200 being 800, yes?
Mm-hmm.
Which leaves no room for y.
Right.
Y would have to be 0, but I can't have a 0 y because then this whole thing would just collapse and be nothing.
Yep.
So here is my constraint, my inequality for x. So now, like you said, I want to find critical numbers, and then I'm going to do interval testing with those. This guy equals 0 when what is true?
When x equals 100.
Yes. When 1600 equals 16x, which comes out to be a nice x equaling 100. Now, I take that critical number, I break up my overall inequality into intervals, yes? So 0 to 100, 100 to 200, and I want to know what is my function, I'll say derivative. What is it doing? What is its sign? What is the sign of a prime on this first interval? Let's say, where's a prime? Right here?
Yes.
Okay, if you take a number, let's say 1. If you stick 1 in for x,
That would be a positive number.
yeah, 1600 over 3 minus 16 over 3 is something positive. So the sign of a prime is positive. Take a number from in here. Let's say, I don't know, 150. 16 times 150 is how much?
900, I think? No. It's a number bigger than 1600.
A number bigger than 1600 for sure.
Yeah.
So I think it's, yeah, it's going to be bigger than 1600.
So it's going to be negative.
It's going to be negative. And if the sign of a prime is negative, it's also positive for this interval, then what a is doing, if you want to be more precise about it, and we're not dealing with any vertical asymptotes, we don't have that complication.
So we can safely say it's increasing from 0 to 100
Yes.
and decreasing from 100 to 200.
Increasing to decreasing, which implies,
We got ourselves a relative maximum.
yes, we have a relative maximum at 100, a of 100. Now the question is this an absolute maximum on this interval?
If that's the only one, and if the endpoint's equal 0, then it's got to be, right?
Yeah, absolutely. In fact, this graph has the same general shape as the last problem. Graph of A, we want to do that here. Here's 0, here's 200, here's my x, here's my A. When x is equal to 0, A is 0, right?
Mm-hmm.
But x is not allowed to be 0, so I got a hole there. Likewise, x is not allowed to be 200, but were x to be 200, I would have 800 over 3 minus 4 times 200 over 3,
Uh-huh.
which would be 0 as well.
4 times, for 200, right?
Yeah.
Yeah.
800 over 3 minus 800 over 3 gives me 0
Yeah.
for there, so I got a hole there. Now we just determined that from 0 to 100, this function a is increasing.
Mm-hmm.
From 100 to 200, this function is decreasing. So this function, this point, is an absolute maximum as well. Now, cherry on top of the sundae here, I want to find the maximum possible total enclosed area. So all I have to do is take 100 and do what to?
Put in for A.
What is A of 100?
I got 200 times 400 over 3, and that gave me 26,666.6 repeating.
2666.6
6 repeating, yeah.
repeating. Feet squared.
Yep.
And there you go. These are word problems that we are making much easier using calculus. Pretty cool, right?
Yeah.
But yeah, now technically these last two problems we could have done without any calculus. Because both are objective functions. In this case A, in the last case P for product, they were both what kind of shape?
Rectangular shapes.
Oh, the graph.
Oh, the graphs. Parabolic shapes.
Yes, they're both parabolic shape, and we well know from algebra and foundations that the graph of a parabola has a max or a min, absolute max or an absolute min at its vertex. So technically, we didn't need any calculus to do this problem. But let's move on over yonder, take a gander at something quite a bit more fearsome. Of course, we will need some calculus. What is the area of the largest isosceles triangle that can be drawn with one vertex at the origin and the other two on the curve y equals 27 minus x squared, provided the latter two form the base of the triangle parallel to the x-axis, and that base must always stay above the x-axis. So let's get a picture for all this.
Okay.
What does the graph of y equals 27 minus x squared look like?
It's a downwards parabola.
So downwards parabola with its vertex at
0, 27.
the vertex at the y-intercept of 27. Right there. It goes like so. Like so. I'm just going to write it y equals 27 minus x squared. And now for my triangle, I got one vertex at the origin. The other two are on this curve, but they're on the curve in such a way that those two form the base of the triangle parallel to the x-axis. So in other words, I can't just pick any 2 points on the curve.
Yeah,
If I pick this point,
reflected on the x-axis.
yes, I got to pick that point as well. Like so. With this right here being my base. That base has to stay parallel to the x-axis, and also it needs to stay above the x-axis.
Okay.
Right? Because if I were to let it go below the x-axis,
Oh, it could be like negative infinity to positive infinity, and it'd be a giant triangle.
infinitely big triangle, yes. So I want it to have those restrictions. So here's one triangle I can draw. Here's another triangle you could draw using this allowance. Here's another one. And the question is, out of these infinite possibilities, out of these infinitely many triangles, which one maximizes the area? Which one has the maximum area? So I'm going to pick this point as a representative. Let's call that coordinate pair x1.
Yep.
Okay. And I'm going to take this triangle out of the parabola just for a second. Have it like so. Here is the base. And here is the height. So both base and height are variable. But regardless of which triangle I'm dealing with, what is the formula for the area of this thing?
1/2 base times height.
Yes, as you well know from your voyages in algebra and geometry, area is 1/2 base times height. Now the question is, what is B and what is H in terms of x and y?
The base has to be.
Let's start with the height.
Okay.
So let's see here. The height is just this distance from there to there, right?
Right. So that's just y.
That is the y coordinate. But now the base in the picture is all of that right there.
Right.
What is all of that right there in terms of x?
So you have that goes from x to negative x. So that would be that would have a length of 2x, right?
That would have a length of 2x. Another thing about it is, look, the way a positive x coordinate is defined is just the distance from the y-axis to that point. So if from here to here has a length of x, then this whole thing has to be a length of 2x. Again, we want positive values because we want positive area. So with that in mind, what is my area function?
That'd just be x times y, right?
Right, 1/2 times 2x times y is a nice x times y. That is the area of any isosceles triangle you can put in here, provided that you know this coordinate in the first quadrant has an xy pair.
Okay.
All right. Now, I want to maximize a, but the problem is a, as it is right now, is a function of two variables. I want to reduce those two variables to how many variables, sir?
Just one.
Just one. How can I do that?
You can substitute the parabola equation.
Parabolish the government. Y equals 27 minus x squared. No matter what your x coordinate is, the y coordinate has to be that.
Yeah.
Has to obey that law. That's what a function does. It sets down the law of the land.
So you can just substitute that in for x times y, right?
Yes. So a as a function of one variable now is going to be x times 27 minus x squared.
Yeah.
Now before I go on, are there any restrictions on x?
Yeah. It has to be in between the first and second quadrant within that graph. So
Yeah, I can't have it be, it can't be equal to this, right?
no.
Or that, because then I'd have no triangle.
Right.
The triangle would disappear. What is this value right here?
That would be the square root of 27.
Right, it's the x-intercept. You set y equal to 0, solve for x. That's going to be the positive square root of 27 right there. Likewise here,
Negative square root.
negative square root of 27. X cannot be equal to either of those.
Is that 3 square root of 3 as well? Like another way to write it?
Yeah. What was that?
3 times the square root of 3. It's another way to write it, but
Could write it that way.
yeah.
Oh, also, it's not just I can get even better on my restriction. It's not just between negative 27 and positive. I'm sorry, negative root 27 and positive root 27. Because I've chosen x to be the x coordinate in which quadrant?
The first
The
quadrant.
first has to be the first. Otherwise, it'll be negative, and I get a
So
negative
x
here.
just has to be from 0 to
Yeah.
positive 27. Square root of 27.
Yes. Can't be equal to root 27. Can it be equal to 0?
No.
Yeah, again, if it's equal to 0, look at this pattern of forming these triangles. They get squishy, 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 squishy right up to the point, and then it disappears again.
Right.
But we want a triangle, so x cannot be equal to 0. So there is a further constraint. Here's my A. I want to distribute, because that makes finding the what much easier.
The critical numbers.
Critical numbers from the
And
derivative. So what is your derivative? What is a prime? What is dA over dx?
It's just 27 minus 3x squared.
27 minus 3x squared, absolutely, my friend. That equals 0. Never equal to define, so it equals 0. When what is true?
X is positive or negative 9.
I mean x squared?
When x squared. Oh, yeah, you're right. X squared is 9. I was trying to.
27 equals 3x squared, so x squared is 9.
So x gotta be 3.
X gotta be 3. Why do I not care about negative 3?
Because we're only worrying about the first quadrant.
We only care, exactly, first quadrant, these values right there. That is in fact a critical number. It makes the original define. Question is, does it correspond to a maximum or a minimum? Or a saddle point? We don't know.
You gotta find out.
We gotta find out. So what do I do next?
Yeah. Find the values to the left and right of that and see if it's positive or negative.
Yes, I take my critical numbers, in this case just plain old critical number. I use that critical number to slice up my domains.
It's very wavy arrow.
That's fine. where this is a wild problem, a cowboy type problem, we can be a bit wavy and wild. 0 to 3, and then 3, 2.
The square root of 27?
Root 27. So, create your little table. What is the sign of A prime? If we take, for example, 1 and stick it in right here to my derivative, do you get a positive or negative value?
That would be positive.
That would be positive. Now let's say from 3 to square root of 27, that's a little more than 5, right?
Yeah.
So you stick 5,
That's
stick that in here.
27 minus 75, that's got to be negative.
That is very much negative.
E.
So this thing goes from being positive sloped to negative sloped. I don't have to worry about vertical asymptotes. So I can go one better in my description and say plain old A is increasing always on this interval, decreasing always on this interval. So were I to graph this, it's not going to be a parabola. It's going to be parabolish.
Parabolish?
Parabolish the government, absolutely. There's my 0. There's my root 27. Of course, I got a hole at 0, a hole at 27. I get a maximum at 3. But notice, is 3 right in between 0 and square root of 27?
No, it's a little more to the left, I think.
It's more to the right.
To the right. Yeah, okay, yeah, because
That's like 5 point something.
Gotcha.
So in this case, it's not a parabola. It's just parabolish.
I see what you mean.
And it kind of goes holes. So this is the kind of shape this graph must take in order to satisfy these requirements here. A is in fact, this point here is in fact a absolute maximum.
The maximum, yeah.
That is 3, A of 3. Final lasso here is to find that value A of 3. I take 3, stick it in either here or here, take your pick. I'll do the latter. What is 27 times 3?
81.
81. What is 81 minus 3 cubed?
81 minus 27, which is 54.
54, and finally units. Do I have it? Nope, just let's say square units.
Square units.
All that to say, behold the power of calculus.
I thought your shoe was gonna fly off.
Yeah.
It's powerful.
No, cowboy doesn't know the shoes.
Okay. Cool. Is that it?
That's it.